Hello everyone and welcome to the channel. So this video is going to be about color spectra and coordination compounds, and in this video we will try to understand that how a particular coordination complex appears to be of a certain color and how to identify it. Okay, now although this topic is very simple as compared to the other ones, so in coordination compound this is one of the most simplest topic, yet question has been asked from here in CSI net exam and the questions were quite confusing. So the type of question or the level, like the way of asking the question is different for the CSI net exam. So we'll try to understand this in detail, and at the end of the video, as I usually do, I will solve questions from your previous year's CSI net exam. Okay, now before starting, before going into the topic, I'd like to tell you guys that all of you who are asking for a video on reaction mechanism of organometallic compound, now the video is available on the Unacademy platform. So the link is given in the description. You can click on the link and you can watch the video in like Hindi or English both. So the language so the video is available in both the languages, and there I have discussed different reaction mechanism, and I'll be solving questions there also. So right now only the explanation is there and questions will be added soon in that course. All right, so now let's continue with the topic. Okay, so let's try to identify. First of all, let's try to understand the basic thing. Okay, see, if you have something, anything, okay, anything present in the nature, how it looks like, how something looks to be of a particular color. Now what happens when a visible light, or you can like say white light, falls on something. White light, when it falls on something, what happens? This thing, like anything, okay, it could be your, like, since we are talking about coordination compound, so let's take it as a complex. So it's a coordination compound. Okay, so it's a coordination compound, and when a white light falls on it, then what it can do, either it can like, see what it can do, if it absorbs all of them, if it absorbs all the light, like if you fall the white light on it, and if all the white light get absorbed, then what we will see, whatever we see is nothing but the reflection, or the left out, what is left out from that is what we see. Okay, what is left out from the after the absorption is what we see. So if this complex absorbs all of the white light, then obviously we won't see anything, so what we will see is black. So if something absorbs all the white light, then it appears black in color. Now if we talk about the reverse of it, like if it does not absorbs, okay, uh, if it does not absorbs anything, okay, if it does not absorbs any part of white light, then what we will see, then all of the light will be reflected back and we will see all of the white light. That means it will appear as white. So this is how something looks black or white. Okay, now what happens if it absorbs certain wavelength of light? Since we know that your white light, okay, so white light or your sunlight, it comprises of 7 colors. Okay, we generally have studied them as Vibgyor. Okay, so Vibgyor, sorry, so Vibgyor. So V is violet, okay, indigo, blue, red, green, yellow, orange, red. So these are the 7 colors in which white light splits, or you can say that white light comprises of these 7 colors. Now what happens if something absorbs a particular wavelength of light? Okay, so if it absorbs a particular wavelength of light, then the emitted wave, or you can say that the wave or the light which we will see, but that will be of different color. So that's why something appears to be of a different color. We will understand this with the concept of with a concept that is called color wheel. Okay, so how this color wheel looks, it looks somewhat like this. Okay, so we will just make it like this. All right, so here we are having, so it's VBGYOR. Okay, so indigo is not, you don't have to add indigo over here. So violet, blue, green, yellow, orange, red. So what happens if you fall white light and if something absorbs violet color of it? If violet color will be absorbed, then the contrary color of the, or you can say in the color wheel, the opposite color will be emitted, or it will look like something like yellow color. Okay, so if some complex absorb violet color, then it will appears to be yellow in color. If a complex absorbs red color, then it will appear green. If a complex absorbs orange color, then it will appear blue, and the reverse will be also true. That means if a complex absorbs blue color, then it will appear to be orange. If it absorbs green color, then it appears to be red. If it absorbs yellow color, then it will appear to be violet. Now, how to identify that which color or which particular wavelength it will absorb? Now, all these things will depend on the splitting. Okay, so we have already understood about the splitting, or how d orbital is split, and in how many, like in the basic of spectroscopy, I have explained that how orbital splits and what are the factors on which the d orbital splitting depends. Now if you haven't watched that video, I'll give you a link in over here, so you can click on the link and watch that video where I have discussed that why the splitting take place and how the splitting will take place. Okay, all right, so let's say we have an octahedral complex like this, and it is splitted into two set of energy orbitals, that is T2g and Eg. Now this is what the energy gap is. So this is the difference between these two level is called the it is called a energy gap. Okay, so now what will happen when you shine a particular wavelength of light, then electron get excited from here to here. So they will absorb a particular wavelength and they will get excited from the ground state, and they will go to the excited state, or it can go to the higher state. Okay, now what will happen if when you stop shining the light, this electron will come back and then it will radiate the light of particular wavelength. Okay, so these are the basic things which you all know. Okay, now what are the things to be noted over here is that if this wave, see, we have few relations between energy and wavelength. We all know that E is equals to h nu. Okay, that means energy is directly proportional to wavelength. Sorry, so if you have higher frequency, the energy will be high, and we know that frequency is inversely proportional to wavelength. Okay, lambda is your wavelength, so we can say that energy is like inversely proportional to wavelength. That means if you have greater energy gap, then the wavelength will be less. Okay, so this energy gap will be reverse of your wavelength. Okay, so let's take it to a simpler level. Let's say that like the wavelength which will depend, like the wavelength which the light will absorb will depend on energy gap. Okay, so if you have higher energy gap, it will absorb a lower wavelength of light, and if we know what wavelength of light it will absorb, then obviously we can understand that which light it will emit. Okay, so for that we need a table, and that table I will show you that how the table looks like. Okay, so this is how the table looks like. So in this table you can see that we have wavelength over here, and we have which color it will absorb and which will be the color it will, like the complementary color, or which color the complex will look like. So if it absorbs less than, like for less than 400 nanometer, it will absorb in UV region. Okay, so that is ultraviolet region, so it will not like show any color, because this is not under your visible region. So that's why the color which the complex will look like will be your colorless. Okay, so it will not look like of any color. Now we all know that the red color is having highest wavelength. So that's why if something absorbs at highest wavelength, that means highest wavelength means the gapping should be least. Okay, I will tell you, like these things we will discuss right now only. So if the wavelength is very high, then it will absorb for red color, and the compound will, or the complex will look green in color. Okay, similarly all the values are over here, we can like check. So these are just an approximate value. You cannot get the exact values for this you can refer to different books, and these values will vary in them. Okay, now what you have to keep in mind is the relative thing, like which is a strong ligand and which is weak ligand, and where the splitting will be more and less. So let's say we have two ligands. Let's take example, and let's say we have FeCN6 and we have FeH2O6. Okay, so FeCN6, and we have 3 minus over here, and here we have 3 plus. Okay, so that means iron is in +3 oxidation state in both the cases. Now you can see that cyanide is a strong field ligand. It's very strong ligand as compared to H2O. Now what will happen in FeCN6? The splitting over here will be more, because a more strong ligand is, the splitting is more over here. So the splitting gap over here, let's name it as delta O. Okay, so delta O value will be over here, and For FeH2O, we will be here also splitting will be there, but the splitting or the energy gap will be less. So let's name it as delta O dash. Now here you can say that delta O is greater than delta O dash. That means the splitting energy for H2O1 in the the complex having H2 as the ligand is less as compared to the splitting energy for that having Cn. Now we all know that energy, this is energy, okay, this is crystal field stabilization energy. So energy is inversely proportional to wavelength. So when I refer it as wavelength, so let's call it lambda, and this let's call it as lambda dash. So this sign will change because these are inversely proportional. If this is greater than this, then the inverse of this will be less than, okay. So the wavelength for this, the absorbed wavelength for this will be lesser than this, okay. So if the wavelength which it will absorb, it will somewhat it will absorb in the blue region, and it will look like somewhat like orange, or it will look like yellow, okay. So that's why most of the complexes which are having cyanide as their cyanide in their complex, they always look either of yellow, orange, or orange color, okay. Whereas when we talk about this one, that is hydrogen, sorry, FeH2O whole 6, here we have wavelength, the wavelength is higher, so it will absorb at higher wavelength, that is, let's say at red. So it will absorb the red color and it will look like green, or it will absorb at orange, so it will look like blue. So it will look like either green or blue, but for this complex it will either look like yellow or orange, okay. So these are certain ways in which you can identify that your complex, how the complex will look like in which color, okay. Let's try to discuss few things and then we will move on to the questions. Now one more thing which I have to tell you guys is the spectrochemical series. So spectrochemical series I have already told you in my previous videos, but in this video also I'm including it because it's necessary to know that which are the relative strength of the ligands, because ligand will play a very important role in the splitting. So higher or the strong ligand is, the more is the splitting. So for cyanide ligand is over here, it's one of the most highest, so it's in increasing order, okay. So iodine is the least one, then bromine, then sulfur, then isocyanide, sorry, thiocyanide, thioisocyanide, then your chlorine is there, then your NO3 is there, N3 is there, fluorine, urea, OH, then oxalate, then oxo, H2O, that is aqua, then EDTA, then your thiocyanate, okay, and then your glycine. This is actually isothiocyanate, this is thiocyanate, okay. This is a glycine, then your NH3 or pyridine, then ethylene diamine, bipyridine, then phenanthroline, then come NO2, then CH3, that is methyl, then phenyl, then phosphines, then cyanide, then carbonyl, and then NO plus. So this is the spectrochemical series, and here you can see that cyanide is one of the strongest ligand. So that's why the splitting is more in case of cyanide or cyano group. The splitting is more, and if splitting is more, so it will absorb lower wavelength, okay. So it's both of the thing are relative, you have to see it like that, okay, because we have already discussed that energy is inversely proportional to wavelength. So energy is nothing but here it is represented as delta O, that is crystal field stabilization energy. Whereas if you'll see or water, it is over here, somewhere here, so it's very weak ligand as compared to cyanide. So that's why the splitting is less over here, so energy is less, but the wavelength will be more, okay, because energy, if energy is less, then wavelength will be more. It's like that, okay. Let's take one question and try to understand it in a better way. Okay, so now let's talk about this two complexes. We have vanadium and we have 6H2 here also and here also, but the oxidation states are different. Here we are having 2 plus, that is vanadium is in +2 state, and here we have vanadium in +3 state. Now I have told you in the previous videos of mine that the splitting depends on the positive charge or the oxidation state of the metal as well. So if you have more positive charge, if you have more oxidation state, then the splitting will be higher, okay. So it means that vanadium plus two will be having lesser delta O value, means the splitting will be less over here as compared to the splitting over here, which is in vanadium +3. Now since the splitting is more, or you can say when the delta O is more, that means the wavelength for this will be less, okay. So if I represent it as this, let's say this one is delta O and this one is delta O naught, delta O dash, then delta O dash is greater than delta O. And if I talk about the wavelengths, then lambda will be greater than lambda dash. That means this will absorb at higher wavelength and this will absorb at lower wavelength. So this will absorb, this complex will absorb at, let's say, red or orange, and it will appear as like red or orange will appear to be green, okay, green or blue. And this one will absorb at lower wavelength, that is either at violet or blue, and it will appear to be yellow or orange. Okay, so it's kind of that you can assume that, like, you can sorry, not assume, but you can like predict that which color it will show. Alright, so let's take this question and try to see that how this concept has been applied. Okay, so the question says that a metal forms two complexes having color green and red, and the complexes can be, so you have different pairs of complexes, and you have to tell which of these is correct option. Okay, now this is already been told you that metal forms two complexes, so you are having, like, the metal is forming two complexes, and the color are green and red. So for this, first of all, what you have to do is just draw quickly this colors wheel. Okay, so VBGYOR. Okay, so just like that. Now since it is having color green, so that means this one is absorbing orange color, and the next one is red, so that means it is absorbing green color. Okay, so this is how they are absorbing. So first of all, understand that which color the complex is absorbing. So this is how it is, how it looks like. If it looks like green, then it is absorbing orange. If it looks like red, then it is absorbing blue. Okay, so now just quickly draw the pattern of the color in the form of wavelength. So it's like, sorry, VBGYOR. All right, so here the wavelength is least and here the wavelength is most. So we have to, we have to focus on this green one and the orange one. Okay, so this one, like, first one is absorbing over here. That means for this the wavelength is high, so wavelength, order of wavelength is like this. Wavelength is increasing over here. When you are going towards red, red color, the wavelength is increasing. So that means orange, it is having high wavelength. Okay, and for green, this one, it is having low wavelength. Okay, so the wavelength for this, for absorption of this, is high, and for this the wavelength, absorption of wavelength is low. Now since wavelength is inversely proportional to energy, that means if it is having high wavelength, if it is absorbing light of high wavelength, then the delta O is less for this, whereas for this delta O is more. All right, since all the things are relative, like if it will be high, delta will be less. If it will be low, wavelength will be low, then delta will be more. Now what you have to see, that in the following complexes in which you are having like delta O less for the first and delta O more for the second. Now we are having which like ligands. So we have ethylene diamine is there, ammonia is there, pyridine is there, water is there, then NO is there. Okay, and then yeah, so these are the ligands which are given in the question. Now if you will see the if you will see the spectrochemical series, then you will find that the orders. Okay, if I write the orders of them, so okay, so the highest one is NO. So NO is highest one, then comes out to be then comes out your NH3. Okay, so NH3 and pyridine are like somewhat similar. Okay, so let's say these are like here. Okay, then actually ethylene diamine is more, so NO, and then comes out to be ethylene diamine, then your NH3 or pyridine. Okay, and the least one is your water. So this is the order of your strength of your ligands. Now the strength of the ligand will decide the delta order. So if the strength of the ligand is more, then delta O will be more, and the strength of the ligand is less, then the delta O will be also less. Now if you will see over here, so in the first one you can see that delta O is more for this, because ethylene diamine is obviously higher, like it is having higher strength than NH3. Okay, so if you will compare, so delta O will be more for this, and for this delta O will be less, means it will be having more splitting, because this is stronger than NH3. Okay, so it will be having more splitting, that means delta O value will be more. So this cannot be your correct option. Let's talk about the second one. So for pyridine and water, here also you can see that for pyridine the delta O will be more, because it is strong, so obviously the strength will be more over it. Okay, so now let's talk about the third option. So in third, Okay, so sorry for the mistake. Actually it was not NO over here, it should be OH. Okay, so it was OH also. NO is not here. Okay, so OH is the least one, so it is least, the like the strength or the, or like the in the spectrochemical series it is having the least strength. Okay, so if you'll see in the this one, this OH will be having lesser value than compared to NH3. So that means this will be like the delta O value will be less for this, and for NH3 the delta value will be more. So that's why this should be your correct option. In the last one also, if you'll see, then this NH3 is there, and this NH3 will be having higher value of delta O as compared to H2, because H2 is weaker, so it will not split that much. The d orbital will not split for H2 as compared to the d orbital which will split for NH3. So like this you have to do the questions. Okay, so like see how you have to approach for the question. First of all, in the question, if it is given that a particular light you are getting for a complex, then see that which light it is absorbing. Okay, now when you see that, when you get that which light it is absorbing, then what you have to see that what is the wave, like what is the relative wavelength of it. Is it higher wavelength or is it at lower wavelength? Okay, then compared to the wavelength comparison, just compare their delta O value, and delta value depends on the like splitting. So the one which will be having more splitting will give you more delta value, and the one which will give you less splitting, that will be giving you less delta O value. Okay, so let's try to find it out. Like let's try to solve few questions which have been asked in CSI net exam, like previous year CSI net exams. Alright, so let's talk about this question which was asked in CSI June 2014 exam, and this was asked for 4 marks. Okay, so the question says that you have a complex of cobalt, that is COL6 3 plus, and this gives you a red color. Okay, and whereas COL-6 3 plus gives you green color, and they are asking you that what can be your L and L dash can be. Okay, so similar type of question we have already done. Let's try to solve it out. So just write it as like, just write it quickly like this. Okay, so for L you are getting red color, and for green, this you are getting L dash, you are getting green. Just quickly draw the color spectra, sorry, color wheel. So V B G Y O R. Okay, so if something is absorbing red color, then sorry, if something is giving, if something is looking for as red color, if something looks like red color, that means it is absorbing green color. So absorbing color I am writing here, so it is absorbing green color. Okay, and similarly if something is looking like green in color, so it must have absorbed red color. Okay, so L dash might have absorbed red color, whereas L has absorbed green color. Now quickly draw the like the wavelength order. So GYOR. So red is of highest wavelength, so that means it has high lambda value. Okay, so it's high lambda, and for this we have low lambda value. All right, now just write the order of your energy. So energy order will be reverse of it, so it will be high delta O. Okay, and it will be low delta O. So that means for L, or the first ligand over here, should be higher, and second ligand should be lower. Okay, now we are having 3 ligands here. If you'll see in the question, you have ammonia, water, and phenanthrolene. So you have 3 ligands, and like just write it down. So this is ammonia, water, and phenanthrolene. So if you write the order of them according to what we have studied in the spectrochemical series, so phenanthrolene is the strongest ligand among these, then comes your ammonia, and then comes your water. So you have to look at the option where you will be having high delta O for the first and low delta O for the second. If you look at the option, the first option, we have NH3 ligand. So NH3 is a strong ligand, so it will be having higher splitting, more splitting. More splitting means high delta O. So it satisfies what we know, like what we have to get. Now for the next one, we have like NH3 and phenanthrolene. Now NH3 is weaker than phenanthrolene, so NH3 should have lesser value of splitting. That means it should have low delta O, but we have seen that it should have high delta O. That means this cannot be our correct option. Okay, because for this NH3 will give you low delta O, but phenanthrolene will give you high delta O. So first one will get low delta O, and second will get high delta O, which is not of the case. Okay, so just neglect this one. Now for the third option also, if you will see, so H2O is weaker ligand, so it will give you lesser delta O, and phenanthrolene will give you higher delta O. So that means they should be low and they should be high, which is not all the case. So this is also not true. For the last one also, if you'll see, so H2O is weaker ligand, so it will give you less delta O, and NH3 will give you high delta O. So that means this also cannot be true, because for our case, for the first one we should have high delta. That means in this case you can see that NH3 is stronger ligand, so it will give high delta O, and H2 is weak ligand, so it will give low delta O. So that's why correct option for this question will be option number A. So in this way you can easily get 4 marks just by knowing the basics of this thing. Okay, let's take one more question. Okay, so this question has been asked in CSI June 2017 exam, and this question was for 4 marks. Okay, so the question says that match the item in the 3 columns. So you are having 3 columns over here. In the first column you are having ligands, like the complexes. In the second column you have the color, of which color it will look, and in the third column you have the wavelength. Okay, so you have to tell which of these are correct option, like which is the correct match for this. Like options are given like A to X, like A green and X means this wavelength. Okay, so it's something like this. Okay, so for this problem, if you'll see that you are having like 3 different complex compounds, and in which or everything is same, just the ligands are different. Like we are having water over here as a ligand, then ammonia, and then ethylene diamine. Okay, and here you are given with the colors, and here the wavelength which it will like absorb. Okay, so now let's talk about the strength of the ligand. So you are having 3 ligands, that is water, ammonia, and ethylene diamine. Now if you remember the spectrochemical series, there I have discussed that ethylene diamine will be the strongest among all these 3, and water will be the lowest one, because it comes like it is a weak field ligand and compared to them. Okay, relatively weak field. Okay, so like this is the order of your delta O. This is the order of your delta O, because this is the order of the strength of the ligand, and it will also correspond to the order of delta O value. That means the order of crystal field stabilization energy. Now if I talk about the order of wavelength, so the wavelength which it will absorb, so the order of wavelength will be the reverse of it, because we know that energy is inversely proportional to wavelength. So this will be like this. So this is the order of wavelength. So wavelength will be highest for water, and it will be lowest for ethylene diamine. So if you'll see, so for water the complex is named as A, so A will be having the highest value of wavelength, that is 675. Okay, so because among these the highest value is 675, so A will correspond to X, so A will be for this, and then B will be for the next one, that is this one, and C will be for this. All right, so this will be the order of like it will be for the respective wavelengths. Now let's talk about the color. Okay, so when we have to talk about the color, that which color the particular compound will correspond to, then here we have already known the wavelength for which it will absorb. And if you remember, in the starting I have shown you a table where it was the wavelength given and the color which it will absorb and the color which it will emit. Okay, so if I show you the table again, so this was the table, and if we match the values, so for X we are having 675. So 675 comes under this one, so this one correspond to, no, 675 correspond to A, so it is A. Okay, so it will correspond to A. Now A will absorb red color and it will look like green color. Okay, so this green will be corresponding to A. Okay, so all this thing you can do with the help of the table. Okay, so if you know the table, then you can do this easily, like exactly. Now the next one is Y will be around 565. Okay, so 565 comes under this. So 565 is here, and this Y is corresponding to the complex C. So that means this range is for complex number C. So C will absorb yellow color and it will look like violet in color. So violet will be C1. So C will look like violet, and obviously one is left, and that is 615. So 615 will come under this range, and this will be your B. So B will absorb orange color and it will look like blue in color. So that means blue will be for B. So that means now let's check the options. So if we'll check the options, then you will see that option number A is like A is connected to 2 and then A is connected to X. So that is matching our options. Okay, so that means this one is true. Now let's check for B. So B is matching to 1, so B is 1, and then B is Z, so B1Z, that is also correct. And for C, C we are having 3, so C3, and then Y, so C3Y. This is the correct option. So option number A or option number 1 becomes the correct option for this question. Now if you don't remember the table, now if you don't remember these values, then how you can assign these? Okay, now for that thing you have to know, like you have to do some, like if you don't remember any value, okay, now up to here you can easily do, like you can assign the wavelengths easily. Now what you have to do, you have to see that which of these is the highest one. So this one is the highest one and this correspond to A. Now if you see the Vibgyor, so if you see the like VBGYOR, so for this the highest wavelength is for red, so that means this will absorb red color. And if you see the correct color wheel, so VBGYOR, so if something absorbs red, it will look like green in color, so A will be green in color, so that you can easily predict, okay, without knowing the values. Now okay, so the first, for the next one is slightly less than that. Slightly less than that means it will absorb like not more, like it is not very less, it is somewhat less. Okay, the difference is only about 60 nanometer, so it will correspond to orange one. So something which will absorb orange will emit blue, so blue will be for B. So like this you can predict, and for the third one it will be violet. So in this way you can easily do without knowing the table also. If you don't know about, if you don't know the values of the table, you can easily do the questions by prediction. So these were few questions which have been asked on color spectra in the previous CSI net exam, and I hope you people understood it well. And that's all for this video, and I hope you people liked it. And one more thing before like ending this video, I would like to tell you that if you are not subscribed the channel, please subscribe it, and do follow me on Unacademy also, because there I'm also posting very helpful videos and which are going to be very helpful for your CSI net exam. And I would like to take your suggestions for the upcoming lessons, that what lessons you want, like from me to, like the next lessons on which topic you want. Okay, and one more thing, like, okay, so that all I already told you, that subscribe. Okay, so just subscribe the channel. So thank you so much for watching. Have a great day. Bye bye, take care.